ENVT lecture, January 18th. So just before we get into this, I'll say that there is a test next Monday, and it will be on topic 1 and the first part of topic 2. So last time we left off, we were talking about water resources, and I wanted to talk a little bit about water properties before getting into topic 2, of which is mostly on water chemistry. So you can see there is the water molecule. You probably know, as everybody knows, that water is, of course, comprised of H2O. And you can see that it's showing the water molecule there. So the oxygen, of course, is connected to 2 hydrogens. And it says, what is the geometry? So this is a bent molecule. What kind of bonding is present? And is this kind of bond strong? I'm going to show you on the next slide. So there is water there. It actually has 2 types of bonds. So first of all, it has these here covalent bonds, which are very, very strong chemical forces. And it also has these dipole forces. So in water, we have the hydrogens, which are polarized, that have a partial positive charge, and the oxygens that are polarized with a partial negative charge. So these positive charges and these negative charges, they can get together and form a dipole-dipole interaction. Now this is a very intense special type of dipole interaction called a hydrogen bond, and you're going to talk a lot more about them in organic chemistry next year. But the important thing about hydrogen bonds, of course, is that they are what gives water its special properties. So I'm going to basically quickly go through these special properties of water and talk a little bit about all of them. So first is the cohesion and adhesion. So cohesion basically means that water sticks to itself, and adhesion means that water can stick to other things, and this is because of those hydrogen bonds. So if you know about plants, you know that plants take water from the roots and they have to bring them all the way up to their leaves, all the way against gravity, and this is because of those hydrogen bonds. So you can see these hydrogen bonds are allowing water to stick together and also stick to the inside of the vascular tissue in plants, and this is all against gravity. And this is really quite incredible if you think about how big some trees are, and the water has to crawl up there all on its own just due to these weak intermolecular forces. Cohesion is, like I said before, water sticking to itself, and as a consequence, water forms beads when it drops. Most people think water droplets are kind of like this shape. That's not true. Water droplets are actually spheres, and that's just the water sticking together. And it's actually a pretty large droplet compared to a lot of other liquids. So cohesion also basically allows water to form almost a little bit of a skin on its surface. And this allows a lot of aquatic insects and spiders to basically crawl along the top of the water surface. You can see there's a water strider there. And I encourage you to go check out this video. This is a basilisk lizard, also known as the Jesus Christ lizard, because it can walk, well, not really walk, it more like runs across water. And it's a very, very cool video. Water also stabilizes temperatures. So we can take a look at that in terms of chemistry. What we're talking about is that water has a relatively large specific heat. So specific heat really just means the amount of heat energy needed to raise water 1 gram by 1 degree. And it's actually a relatively large number if you compare to a lot of other chemicals out there. And liquid water in particular has a relatively high specific heat, which means it's really good as a coolant in a lot of industrial processes, but there's actually a lot of biological phenomena that take advantage of this particular property of water. For example, here's basically a geography example. So if you take a look, this is actually showing California. So you can see there's Los Angeles, and Disneyland is in there somewhere. If you've ever been to California, you know it's a warm place, but it's pretty nice. It's not a desert, but if you go inland over here, in these areas over here, it's actually very hot and very desert-like. And so what is going on here is that the ocean is actually absorbing a lot of heat that actually has an effect on the land and makes the California coast a really nice place. Water also stabilizes temperature in your body, and that's why we sweat. Hopefully we don't sweat that badly, but the water gets released, the water evaporates, takes the heat away from it, and it's an important part of our homeostasis. Water also expands when it's frozen. This is really important if you were a fish. So first thing it says here, it says the density of the water changes with temperature. So what is density? So density is basically the amount of mass per volume. So if you take a look at what happens with water in the various forms of matter, in the vapor form, the molecules, they're not even really interacting, they're kind of just far away. In the liquid form, the molecules, they're kind of touching and they're interacting, but they're also slipping around a little bit. But as the temperature drops and gets down to 0 degrees Celsius, they start to lock into place, and these hydrogen bonds here form, and they lock into place, and they form basically kind of a hexagonal type of shape of molecule. And this actually pushes them apart a little bit. And so the density of water at 0 degrees is actually less than the density of water in the liquid form. I actually have some numbers here, maybe on the next slide, but you can see that actually at 4 degrees Celsius, so right here, that's when water has the most density. So the consequence is that ice floats, right? Just another picture showing the cage structure of the water molecules. So it says here, this is the reason why aquatic organisms survive the winter in frozen lakes. So lakes do not freeze from the bottom up. That would be really bad for fish. Instead, they freeze at the top. And in the winter, the fish can survive under the ice, munching seaweed and whatever else they find. And that's a very, very good thing for them. Little video here just showing you something funny. It says the reason why penguins have so much fun. And boom. I'll show that one more time. I have another penguin video for you just for fun, the wacky penguins. So I'm pretty sure these are not real videos. They're some sort of computer animation, but anyway, they're kind of funny. Hope you enjoy the videos. Water is also a powerful solvent, so we're going to talk about that in the next unit. But basically, it's because water is able to dissolve many, many different types of solids, particularly anything that's polar or charged. So you can see in this case, they're showing the solubilization of sodium chloride. So sodium here is a positively charged ion, and that can interact with the negatively charged oxygens. Chloride is, of course, a negatively charged ion, and that can interact with the positively charged hydrogens. So water can interact with them and solubilize many, many things. Water also has acid and base properties. So again, much more on this in our next unit when we talk about water chemistry. But acid and bases really have a lot to do with whether things can donate or accept hydrogen ions. So this is a hydrogen ion right here. We're going to talk a lot about pH. pH is, of course, the measure of those hydrogen ions, and you're going to talk about them in this week's lab. So you're going to get a chance to use and calibrate a pH meter. There's the pH scale. Hopefully you're somewhat familiar with it. The neutral is, of course, pH 7, and that's pure water. Acidic includes a whole bunch of different beverages, such as Coca-Cola, root beer, tomato juice, orange juice, and so on. And of course, anything that has the word acid in it, like battery acid, of course, is going to be acidic. Alkaline things include human blood, which is just barely alkaline at around pH 7.4 to 7.6, and a whole bunch of cleaners and other things. Last thing to mention is that water can be viscous. So what does that mean? Viscous means that there's a resistance to flowing. And so this is going to be important when we get up to, I think it's topic 5. We're going to talk about water flowing through pipes. And water will interact with the pipe. There'll be friction with the water as it interacts with the pipe material. So you can see in this diagram here, they're showing that liquid in the center is flowing faster because there is less friction. So more on that later. I think that's topic 5 and definitely lab 5. So test yourself. What property of water gives it its unique properties? So hopefully you have chosen C. It's very important to remember that water can form hydrogen bonds, and this is the secret to its success of doing what it can do. There are, of course, other water properties that may or may not come up in this course. We're definitely going to talk about hardness, which is how much magnesium and calcium is dissolved in the water. And of course, this causes scaling on plumbing and other things. We're going to talk about conductivity, dissolved oxygen, which is really important for biological organisms. We're not going to talk about rainbows, but rainbows is something that water can do, which is kind of cool. So it's worth mentioning. If you want to know a little bit more about the properties of water, you can check out this video here as well from the Amoeba Sisters. So lastly, I just wanted to mention that at the end of most of my topics, or sometimes as an extra document, I will have study questions for you. So do take a look at them as you prepare for your first test. And there's a few more. And some last thoughts. Water quality is a very multidisciplinary science. It uses chemistry and biology, physics, all sorts of different things. So hopefully you'll find some of the things that you've learned in your other classes useful for this class. So that's it for topic 1. What I'm going to do now is start topic 2. So let me just switch to topic 2 for you. So topic 2, we are going to talk about water chemistry. And after today, we're going to start to be doing a lot of calculations. So in class, I showed this video here. You can check out the link and watch it. It's about 3 minutes long, I think, found on Yahoo News. And it's kind of an interesting commentary on Brita and tap and bottled water. And really the finding is that there's not a lot of difference. Some people are mistrusting of tap water, but a lot of bottled water is basically tap water that has been maybe filtered just a little bit more, but not really that different than tap water. So here's a bit of an outline of topic 2. And what I'm hoping is by next day's class is to be able to cover A and B and maybe up to a little bit of C, and that's what's going to be on the first test. I will know, of course, on Wednesday what is going to be covered on the test. There's also a few references here I want to point out. I'm going to try to put the most important references at the beginning of all the PowerPoints so that if you need some additional material to read, you're going to have that available to you. So some more definitions. Hopefully this is like grade 6, you know, what a solution, a solute, and a solvent is. In this class, of course, we're going to be talking about water. So the solution will be made out of water, water being the solvent, and the solute will probably be things like ions or dissolved gases. So of course, there are lots of things that can be dissolved in water. Here's an introduction to them. We'll cover all of them as we go along. So I'm going to skip through this slide quickly. So first question is, what is an ion? Good question. An ion, of course, is a charged species. So it is either lost an electron or two, or it's gained an electron or two. It says here, what are some examples of ions that can be found in water? And so we talked about some of these in class, and you can see there are a few listed here. We, of course, have our cations. Cations are positively charged, and we have our anions. And anions are negatively charged. So here's a few. I think we covered most of these in class. I think one of them that is not on this list, of course, is F, which is fluoride. So if you don't know these particular ions, it's a good time to learn them now because we're going to be talking about them and using most of their short forms over the semester. One more that I see is not on there is, of course, ammonia, which is NH4+, so ammonia. So if you're wondering where some of these ions come from, much of where they come from is actually basically the geology of the area. You can imagine as rivers flow along and lakes, they'll absorb what's in the rocks and the soil and whatnot. And you can see some of the lists of where these things are from. Of course, Neil O'Donnell, of course, knows a lot about these things. And sometimes I talk to him about the sources of some of these ions. Notice that sodium, some of it's from pollution, and often we're talking about things like, well, oil sands processes or putting road salts down during the winter. but there's quite a few sources that can actually introduce sodium to water sources and soil, of course. Here's some anions. Anions are negatively charged, and we're going to be talking a lot about bicarbonate and carbonate, so we'll get to that. So I already talked about the ionization of sodium chloride, so I'm going to skip over this slide here, but do review these things carefully if you are not sure what I'm talking about. I'm going to skip over this slide here because we're going to come back and talk about these. So where I finished off on today's lecture in class was just basically introducing some formulas. And some of these you've probably seen before, and maybe some of them you have not. So probably the one most people are familiar with is molarity. So molarity is the amount of moles per liter. So that's the units. Molarity is moles per liter, or sometimes we use a big M. Do not use a little m. A little m is a different unit. It means meter. So make sure you do get your units correct. We will come back to molarity. Like I said, I'm going to, next class, I'm going to do some sample questions for each of these, or at least the important ones. One you may not have heard of is molality. This is kind of an old school unit of measure. You can see it's basically moles per kilogram of solution. So you don't see that too often anymore, but once in a while you'll order a chemical and it'll be quoted in molality for some reason. Something else is percent. So this is pretty commonly used in certain industries where they'll talk about a percent solution. So they might say a 1% saline solution or something like that. And usually this is a mass per mass. Sometimes it's volume per volume. Sometimes it's volume per mass. It doesn't really matter. We'll go over some samples of this next day. We can see percent mass is percent mass of solution divided by total mass of solution times 100, and that will give a percent, of course. So something even smaller than a percentage and a hugely very, very important unit is parts per million. So it's important to know that a part per million is 1 milligram per liter, and we're going to show you why in next lecture why it is 1 milligram per liter. It's also 1 microliter per liter as well, and we're not going to worry too much about microliters in this course, but if you do see that little symbol, this one that looks like this, that's a micro. Sometimes parts per million are not small enough, so it's common to see parts per billion, and every once in a while we might see parts per trillion. I've only ever seen that once, but parts per million and parts per billion are going to be really, really important in this class. And then lastly, we're going to also talk about something called milliequivalence. It's a little hard to get into that right now without going into a big lecture, but we're going to talk about that next day. Milli, of course, is part of the metric system, means 1/1000th. And equivalence really just means we're talking about the valence. So it's kind of like millimole, but we're looking at the charge on these things as well. And then, of course, per liter. And this is useful chemically. It's used pretty widely in the water quality industry and also, believe it or not, pharmacology industry. So I think that's it for today's lecture. I'm not sure what I will do in the future in terms of recording lectures. It seems that doing it in the classroom, the quality did not turn out very well, so this is why I'm doing it this way.